Hi everyone. Today we're going to be doing goal number 1, which deals with simplifying complex expressions, and we're going to be doing adding, subtracting, and multiplying on this page, and we'll do division on the next, and then we'll have a part 2 of the videos as well later on. First off, when we look on our calculators, we're talking about complex numbers. These are imaginary numbers. So recall, mathematicians didn't like the fact that when we were to do problems, and we would do the square root of a number. So let's say I did the square root of 25. I was able to get a value of 5. But when I tried doing the square root of a negative 25, we got no solution. What mathematicians came up with was a way to actually do this, and this is actually having to do with imaginary values. So what we're going to do is, now that we're going to work in the realm of imaginary, we're going to have to change our calculators to now be a plus bi. That's the standard form for imaginary values. Okay, real and then imaginary. Let's quit out of here. And now when I do the square root of 25, it still doesn't change because 5 is always going to be real, and we can do it. However, the square root of negative 25, instead of doing that and getting an error, now we're going to get 5i. Why is this? Well, that actually stems from a golden rule when it comes to complex numbers, is that I squared is always going to be equal to negative 1. Now, let's apply that to a problem here, okay? If we take the square root of 144, we know that this negative right here is the same as a negative 1 times 144. That means that if we apply our rule right here that negative 1 is equal to I squared, this is the same thing as rewriting it as I squared times 144. We've learned in the past that when we do square roots of a variable squared, we're going to get just an I, and then square root of 144 is just 12. So it becomes 12i for the answer. It's no different than if we had just done square root of 144, which would have been 12, but because it's a negative, we're going to have 12i. Okay? Same thing will hold true with the problem where you have to do some simplifying. We know that the negative is the same thing as a negative 1. 128 is not a perfect square, so if we broke this up into separate parts, this will be 64 times 2. So now if we take each part, and let's change this negative 1 first to an I squared. If we take each part and do the square root of each portion, I squared will just be an I, square root of 64 will be an 8, and then square root of 2 we can't do, so it's going to stay as the square root of 2. And this will be our final answer. Now traditionally, the way you'll see standard form written is this I would actually come afterwards, so it would be 8, square root of 2, and then an I. That's the way you'll normally see it, but the way I do it, I keep the I in front just because I don't want the I to look like it's inside the square root. Okay? So now let's start applying it. Hopefully you understand this concept, and we can actually end up just skipping this middle step right here because it's just extra work to write the negative 1, then the I squared. So let's see what it looks like in a little bit faster action. If we look at this next example, we're going to have 3. The square root of 25 would just be 5, so square root of negative 25 will be 5i. Square root of 7, and then we have square root of negative 4 is just going to be 2i. And then the nice thing about imaginary numbers is they're not very complex, despite the fact that they're called complex numbers. If we just add these together, this will be 10 plus 7i, and you are done. Okay? Based on this example, where it's just combining like terms, the next example here of 3 plus 5i plus 9 minus 12i, the operation here is addition, so we're just going to combine like terms again, and we're going to have 12, and then 5i minus 12i, we're going to have minus 7i. So this is our final answer. This is where it gets a little more complicated when we're doing multiplication. What's going to happen is we're going to take these and multiply them together, just like you normally would. You know, 4 times 10 is 40. 4 times negative 2i is negative 8i. 3i times 10 is 30i. And then 3i times negative 2i is going to be negative 6i squared. Now let's combine the like terms. We have 40 plus 22i minus 6i squared. Okay? Now, can we simplify this further? Absolutely. take this value right here and let's look at it on a larger scale of what we know. We know from the golden rule that I squared is the same as negative 1. Since I squared is the same as a negative 1, this is really saying negative 6, and then that I squared will be a negative 1. What's a negative times a negative? It's a positive. So that means that we end up with 40 plus 22i, and this will be plus 6. That means my final answer is going to be 46 plus 22i. Okay, so that one little change right here is what's going to really be different about these problems than what we've done in the past. So let's take a look at the next part here where we have 7 plus 4i squared. My recommendation is write it out first. Okay, so we have 7 plus 4i times 7 plus 4i. That means we end up with 49 plus 28i plus 28i plus 16i squared. Okay, this is 49 plus 56i. And then we have to talk about this value here. We just learned in the previous problem that when we have an I squared, that's the same as a negative 1. So we have a positive 16 times negative 1. That means that we're going to have a negative 16. So if we simplify this, we end up with 33 plus 56i, and this is our final answer. Okay. To continue on with this, let's take it now to division. Okay. When we're talking about division, before we get into those kinds of problems with division, let's look at a couple of examples here. First thing I want you to notice is that this one written out looks like the difference of two squares. Just like right here it looks like the difference of two squares. Watch what happens though when we multiply this out and it's the difference of two squares. If I multiply this out, we end up with 100 plus 30i minus 30i, and then minus 9i squared. 100 is the value right here. The 30i minus 30i will go ahead and reduce to be nothing. This minus 9i squared. Okay, again, I squared is synonymous with negative 1, so negative 9 times negative 1 is positive 9. That means the final answer is 109. Notice all of my imaginary values disappeared when it looked like the difference of two squares. Will that always hold true? Well, let's try another example and see. If we try 7i times 7 minus I times 7 plus I, we're going to get 49 plus 7i minus 7i minus I squared. This will be 49. These will simplify out to 0. And a minus I squared. Again, I squared is negative 1. So the opposite of negative 1 would be positive 1. So this will just equal 50. Look at that. It disappeared. So how does this apply then in terms of problems where there are fractions? What we know is that with fractions, you can have no value in the denominator that's not a rational value. I'm sorry, that is just a regular rational value. So I can't have a fraction. I can't have a square root. I can't have an imaginary. I can't have a decimal. So how do we get rid of the imaginary? We're going to apply what we just learned up here with these difference of squares. We're going to write the denominator so it looks like the difference of squares because we know that that will make the i's cancel. What we call this is the conjugate. The conjugate is the value that we would multiply by to make it its opposite or its inverse. Okay, so 4 plus I, if I want it to be the difference of two squares, I would do 4 minus I. And whatever we do to the denominator, we have to do to the numerator as well. So we're going to go 4 minus I here. Now it's just a matter of multiplying this out and then reducing it. So we get 20 minus 5i for the numerator plus 8i minus 2i squared. And for the denominator, we get 16 plus 4i minus 4i minus I squared. Simplify each one of those parts. We end up with 20. This will be a 2 here, sorry. So we get 20 plus 2 will be 22. Negative 5i plus 8i is going to be 3i. And for the denominator, again, negative I squared, it's the same as saying the opposite of negative 1. So that'll be 17 These will cancel, so 16 plus 1 is 17. And this will be our final answer. Okay? Feel free at any point to go ahead and pause and try these problems on your own. But here are 3 examples. Write them out first, and then you can go ahead and check the answers. Okay, but let's go through them. So for the next one here, 6 plus 5i over 3 minus 2i. The conjugate of 3 minus 2i is the one that would make it look like the difference of 2 squares, so 3 plus 2i. Multiply the top by 3 plus 2i. Okay. Simplify this, so now let's multiply it out. We get 18 plus 12i minus 15i plus 10i squared. And this will be 9 plus 6i minus 6i minus 4i squared. Okay? This will become, the positive 10i squared is the same as a minus 10. So we have 18 minus 10, which will be 8. And we have minus 3i. 9 plus 6i minus 6i, these will cancel. The negative 4i squared is a positive 4. So 9 plus 4 means that we have 13. So we have 8 minus 3i over 13. And then 2 more examples. 2 plus 5i, its conjugate would be 2 minus 5i. And do the same to the top. All right. Multiply this out. I'm going to skip some steps now because hopefully you've seen the pattern that if we take the first 2 terms here, oh my gosh, you can't even see it, sorry. If we take the first 2 terms here, 2 times 2 is 4, 5 times 5 is 25, and if you notice, we always added the values together in the other ones, so just add them together, we'll have 29 for the denominator. And on the numerator, we're going to have 8 minus 20i minus 2i plus 5i squared. 5i squared is the same as minus 5, so we have 3 minus 22i over 29. And then last one. Conjugate of 1 plus I is going to be 1 minus I. 7 plus 3i is going to be multiplied by that 1 minus I. And if we go ahead and multiply this out now, on the bottom, again, 1 times 1 is 1. 1 times 1 is 1. 1 plus 1 means that we're going to have 2 for the denominator. Feel free to multiply that out if you didn't follow along with that. We end up with 7 minus 7i plus 3i minus 3i squared. This, again, is a plus 3. So we have 10 minus 4i over 2. Now, if you notice, since these are all fractions, the question always comes up, can we reduce them? 22, 3, and 27 have nothing in common, so we can't simplify them. 8, 3, and 13 have nothing in common, so we can't simplify them. 3, 22, and 29 have nothing in common, so we can't simplify them. However, 10, 4, and 2 do have something in common. They are all divisible by 2. So if I divided each one of these by 2, I would end up with 5 minus 2i over 1, which would simplify now to be 5 minus 2i, and that's it. That'll be our final answer. In order to reduce these, you have to remember that every one of the values has to be divisible by something. That's it. Hopefully this helps. Look for part 2 on how to do extension, which is higher powers of complex numbers. Talk to you later.